Okay, let's talk about KVL and KCL, Kirchhoff's voltage and current laws. So KVL, let's put a little, where can I write? I guess let's try over here. So KVL, Kirchhoff's, I'm not writing very well, voltage law says when you add up the voltages around a loop, the total is zero. It's like you climb up a mountain, you go over, you come back down, you come back to the point you started, your overall height is still the same as when you started. The difference is zero. So the potential difference going around a loop is zero. Alright, so that's Kirchhoff's voltage law. KCL is Kirchhoff's current law. It says all the current coming into one spot, into a node, right, if we have a bunch of wires coming in, all the currents in equal all the currents out. What comes in, what goes in, goes out, right? And so there's no charge gets lost in the nodes or lost in the wires, no electrons getting stuck, right? That whatever comes in goes out, all right? And so we can add that if we want to make positive going in and negative going out, we can say they sum to zero, or we can just, I like to usually do it, current in equals current out. Okay, so we got this little circuit here, got some different kinds of elements that some we talked about, some we haven't, but it doesn't really matter. We're just going to, first thing says name all the voltages and currents. So to name all the voltages, we're going to pick a name for them, but then we've also got to show what side is positive, what side is negative, because voltage is always, remember, voltage is really potential difference, right? Change in potential difference across something between two different points. And so so the voltage sources already kind of have their names, right? Remember the positive, these are just drawn with plus and minus already in them. Remember when we draw them as a battery like this with the long, short pieces, the long side represents the positive and the short side represents the negative. All right, so let's just give these other ones names. Let's kind of make their pluses agree with the source pluses, although it doesn't agree with that one, but anyway. And so let's just call this, say, V1, V2, V3, V4, I don't know, let's just do this, V5. And so there's not really a huge right or wrong with this, because if we did, say, get it wrong, and the voltage is the opposite, should have been minus here and plus there, all it says is we'll just get a negative number for V1, which just means, okay, it's really actually higher on the other side from what we said it was. All right, so we'll do the math correctly, write the equations based on what we draw here, what names we give them, and we're all good. Okay, currents now. Currents, we want to use the passive sign convention, which says current goes into pluses on loads and into out of pluses on sources. So for example, this battery is a voltage source, right? It's producing voltage. It's like putting energy into the circuit. So we would make the current in this branch come out of the positive of the voltage source. And so let's just call this, I don't know, I1. All right. Similarly here, this source has a positive on that side, so we'll draw the current going this way, call it I2. And so I kind of drew it going into the minus, but if we continue on, remember current goes through things, right? So the current would be coming out the minus. So think of the plus part of any kind of device as its energy place, right? Or wherever we're studying it. And so if current comes out of the plus, that means that thing is adding energy into the system. If current goes into the plus, that means that thing is sucking energy out of the system. And so this is especially important for Ohm's law. If we want to write Ver for something, then, which we can only be written for resistors, then we have to have, if we want everything to be positive, then we have to make the current go into the plus. So the current up here, we'll call it I3, has to go into the plus of this resistor. The other passive devices, same story. So let's make the current here I4, and that, let's see, and then this guy has a current going down like this. We'll call it I5. And that's really all the current, well, we need a source current here, I6. think that's all the currents we need. I say, well, what about this guy? He doesn't have a current. And what about this guy? He doesn't have a current. But they do, right? Because the current, these two guys, these two are in series with each other, right? So current comes through, this is a diode. Current comes through the diode. It has no choice. It has to go through the capacitor, right? There's no branching, no way for it to go anywhere. So I4 is also the current in V3, right? All the current that's here has to go here, so it's the same current. So if we named another one I7 or I7 here, I7 and I4 are exactly the same thing. I guess we can do that. Let's just get crazy and put one for everything. Same story here. This source and this inductor are in series, so but we could name this I8. Okay? And that's pretty much it. So why don't we have current in these guys? Well, what are these guys? If we look at them, there's no element in here, right? So all of this wire is really just one connecting place, one node, right? If it were Play-Doh, we could mush it all together and say that's just one point, right? So the circuit is kind of squished together into one point, kind of got a top circuit and a bottom circuit almost, right? With a node, one big node in the middle. So we don't tend to break up the current inside of nodes, or don't put currents in the nodes and tend to break it up. Although we could, if we wanted to know the current in this piece, if it was actual separate wires and we wanted to, we could. But as far as the circuit works and as far as solving the circuit, it's an extra thing. So we don't really want to do that. Let's jump to, so we've named all the currents and voltages and a little extra actually. And so let's look at KCL for a minute. Well, we can do KVL first, I guess. Write 5 KVL equations. Kirchhoff's voltage law says, start at one point, go around in a closed circuit, closed branch where we know the voltage is around, or where we have names anyway. We add them up, and the voltage comes to 0. So the total voltage is 0. So how do we add up voltages? Maybe we don't need that because, anyway, we kind of need to know, well, I have another question I should have put on here. How many nodes are in this circuit? So how many different connecting places are there? So we already circled this big red one, right? But then we've got this one. It only goes this far, right? So a node is just as big as you can, or kind of defined as far as you can go, as much wire without running into something else, right? So that node's that big. This node is here. And then, let's see, we have this node down here. So nodes in general are places where things come together, but they're only as big as, or they end when you run into another element, right? So we have another node here. So in this circuit we have 1, 2, 3, 4, 5 different nodes, right? So when we do KCL, we're going to do KCL at a certain node, but for KVL, we're going to go around a loop, right? So we could go around this outside loop, we can go around this loop, we can go around here, around here, around here. So it says 5, so let's do one for each of these kind of loops here, and then we'll take this big path here. We could do a path through the middle, we could do a path, anyway, we could do a path here, path through the middle, path around this way. There are actually more than 5 paths we can do. In general, when we're trying to solve a circuit, however many variables we make, we have to write that many equations. Right? Laws of algebra tell us, or laws of math tell us, that if we need 5 variables to solve for, we have to have 5 equations, 5 independent equations, which could be tricky as well. Okay, so we're not looking to solve here right now, we're just trying to get equations. So let's practice. So let's just do this, we'll call it the top left loop, KVL. What do we get? So we're going to start here, we're going to go around. So just think of you're walking around this wire and you come to a side. Whatever side of the voltage you hit when you come to an element, we hit the negative there. So I'm going to say negative V1. Right? We're adding up voltages, so don't put I1 in a voltage equation. Right? It's all got to be voltages. All right. So we go through there, and so we go minus to plus. So it's minus V1. Then we come here. And we hit the plus side first of this, so it's going to be plus 5 volts coming on in. You go out the minus sign, come through and we're going back along this wire. We got to where we started, so we say equals 0. All right, that's KVL for that loop. Let's do top right loop KVL. All right, let's just start in this middle point. So we're coming up here, walking along. We hit the negative side of this 5 volts. So we're going to have negative 5 volts this time. Coming around here, we hit V2, right? We come to the plus, the side of this diode that's labeled with the plus first as we're walking around. So it's going to be plus. We called that one V2. Coming around. So this is where you see you have to make sure you put the plus and minuses when you name the voltages so you can write the equations correctly. Or so you know how to write the equations. And then coming along here, we get to this capacitor. We hit the positive side first, so it's going to be plus V3. Walking on through to the negative side, continuing on this path. We got to where we started. So anytime we're walking on just wire, we're not adding up any voltages, even though in some examples we can calculate the resistance of a wire if we want to, but normally it's very, very small. So usually we just ignore the resistance of the wires, and then we come back, so we're 0. So equals 0. Because we came back to where we started. We started at 10 feet above sea level. We went up and around and came down and over. We came back to right where we started, so the difference is 0. We're still at 10 feet above sea level, so the potential difference is 0. Okay. Let's do bottom left loop, KVL. So starting here, not much happening there. Nothing, because we're just on wires. But then we hit something finally. We have we get into the plus side of V5. Continuing on, we hit the plus side of 3 volts. And then we come back on the wire. We get to where we started, so we say equals 0. And then let's do bottom right loop. Get its KVL equation. Start here in this little green node. We go up, we get negative 5 volts. Nope, not negative 5 volts, that's V5. Negative V5. Negative V5, continuing around here. We hit the plus side of V4 first. Then we come to the 4 volt thing, but we're going to come into the negative side first, so it's going to be a minus 4 volts. Coming on through to the plus, come back to where we started, equals 0. Okay, so that's 1, 2, 3, 4 KVL equations. I said to write 5. So let's go around the outside. KVL around the outside. Okay, so let's again start here. Going up, nothing. We hit V1, so we hit negative V1 because we hit the minus sign side first. Plus V2, as we hit the plus side of the diode first. Coming on down, plus V3. Coming on down the far side, plus V4, getting lots of positives. Coming in, but the negative side of the voltage source, so minus 4 volts. Continuing on to where we started, we come into the plus side of this voltage source, plus 3 volts. Come out the minus sign, back to where we started, equals 0. Alright, so now we've got a whole bunch of equations. We have actually 5 voltages and 5 equations, so we could solve for all of these voltages if we wanted to, right? Some of them are easy. This one, V1 must be 5 volts, right? This one, V5 must be negative 3 volts, so forth. So we can, some of them, if there's only one variable in the equation, they're nice and easy, you can solve. If there are 2 variables, you'll have to solve for one, eliminate things, put things together. These 3 equations would have to work together to get 2, 3, and 4, but we could do it. But we're not going to take time to do it right now. Right, but the point is we've got equations, and if we wanted to, we could do a different loop to get another equation if we needed it. But it asked us to get 5, we got 5. All right, so that was part B. Part C says write 3 KCL equations. And, all right, so we might write a few more than 3 because I want to do some boring ones. So remember I said we didn't really need this I7, right? But let's do KCL at the orange node, right? So the whole node, remember, as we go to the different 2 pieces that it connects to, or all the pieces it connects to, and that's all inside the node. So we're going to say the current into this node equals the current out of this node, right? In equals out. So what's coming into the orange? Well, what's related to it is I4 and I7 are related to it, right? So I4, if we back it up, because remember it goes, these currents flow through the whole branch that they're on. You can draw the arrow anywhere you want, anywhere. And so it's coming in to the node. So I4 is going in, and nothing else is coming in, but I7 is coming out, right? Again, we back it up. I guess we could I7 is coming out of the node. Interesting. The way I drew it, it looks like I4 is inside the node. But anyway, I4 is really in this element, right? If we're taking the node as a separate thing, I4, we drew it to be part of V2, or the diodes, to go along with V2 for naming the diode. And so it would be the current going in. It is a little confusing looking. And then I7 is the current coming out. So I4 equals I7 is all you get for KCL at that node. And so I mean, you could do this, you can write that equation, but it doesn't give us any more information. We could have just looked at, like I said at the beginning, we would just call it all I4 because we know they're in series, and we know that that we're going to get this equation. If we write KCL at that node, it's just going to say in equals out, I4 goes in, I7 comes out, and there's nothing to it. Same kind of thing if we wrote KCL at this, what is it, pinkish node, right? I8 comes in, I1 comes out, and so pink node, KCL at pink node says I8 equals I1. And so I would say don't even name I7 and I8, just use I1 and I4 for that. But if you accidentally name two currents and they end up being the same, you can still figure it out. Again, we name the current in the node. So the little bit of confusion caused me to pause here. The I4 really should be named back here, right? Because it was a current for this one. Okay. All right. So those two are really kind of the boring KCL ones that we don't really give us much information. So the more useful KCL equations are when we have at least three currents entering or leaving a node. All right. So let's do KCL. Let's start with the blue node. All right. So looking at the blue node, we got I3 going in this resistor going that way to the left. We got I6 going up into the node, right? And we got I4 going through the diode this way. All right, so we've got in, I4 is going out, I3 is going out, but I6 is going in. So if we're doing in equals out, I6 equals what's coming out, I3 and I4. So we add them up, I3 plus I4. So the KCL equation for the blue node would be I6 equals I3 plus I4. Okay? Let's do KCL at the big red node. All right, because it's got a lot of pieces. It's a big node, right? So it's one of those that tricks people, but let's kind of look at it. So I2 down here, so we're going to go till we get to an element. So I2 is going to the right into the voltage source. So I2 is out, but I3 is in. So let's just start writing all the ins. I3 is in. How about I6? I6 is going up through the current, through the voltage source, so it's out. I5 is going down in the resistor, it's going out. I4 is coming in, right? It's coming through the capacitor down. So I4 is in, so let's add I4 to the inside. And then that's maybe the only one, because I1 is again coming down into the resistor, so I1 is out. So the only two going in are I3 and I4. And then let's just count how many currents we have. 1, 2, 3, 4, 5, 6. We have 6 currents altogether, and it looks like 2 going out, so we better 2 going in, so we better have 4 coming out. So, like I said, I6 is going out, and I2 is going out, and I5 is going out, and I1 is going out, and we already said that I4 was coming in. So 1, 2, 3, 4, 5, 6. So we got all of our currents, and we've decided which ones are going in and which ones are going out. Put them on the same side. This is the ingoing side. This is the outgoing side. So what comes in goes out. All right, one more KCL equation. Let's do KCL at the green node. So I guess another good reason not to name currents more currents, because then you have to write more equations, right? However many current names you give, then you have to write that many equations also. So, all right, green node, excuse me, has 3 different things connected, or it connects 3 different things. I2 comes through the voltage source, and it goes into the green. So we say I2 is on the inside. I5 is also coming in. Well, and I1 is also coming in. Everybody's going into this node. What's coming out? Nothing. So we put a 0. Right? So if there are no outs or there are no ins, you just put 0 on that side of the equation. All right, so there we go, 3 KCL equations. And so that's that problem. Down here, let's just do this little practice thing here. We got a piece of a circuit here, so we'll assume there's stuff out here, maybe resistor, source, whatever, out on all these branches, and it just tells us we've got some current IX going in here, 5 amps going in here, 2 amps out, 10 amps out. So it wants us to tell it what is IX. Well, we're going to do KCL at the node. That one we can't see very well. Maybe I should just use regular pencil. All right, so what does KCL tell us? Ins equals out. So what's going in on this node? We got IX is going in. We got 5 amps is going in. That's all the ins. So ins equals, adding up the ins equals adding up the outs. So we got 2 amps going out and 10 amps going out. All right, so IX plus 5 equals 12. So IX equals 12 minus 5 equals 7 amps. So IX is 7 amps. All right, so KCL, KVL, they tell us how to write equations describing the circuit, and then we can use that with algebra to figure out different things within the circuit, voltages, currents, what have you. Okay, let's look at this loop, or this one that's asking for VY and I. Okay, but let's go, well, first off, what is I? Well, it's a series circuit, right? All 3 of these things are in series, so there is only one current. Things in series all have the same current, and to make Ohm's law work in a positive way, we're going to make the current go into the plus of this resistor. So we call that I. Okay? And so that's good for this voltage source, but it's bad for this voltage source because it's coming in, current is coming into its plus, but we can only name one current for the loop, so it might be backwards for something. So we'll probably get something having a negative sign on it, right? And so we don't, like I said, we only have one current, so KCL doesn't do us much good. I goes into this node and out of that node. I goes into this node, out of that node, right? So there's all the same I. So KCL equations aren't going to help. Let's do KVL. So KVL, we got one loop. KVL around the loop, let's just start here, go around, -10 plus VY. Continue on, walking around, we hit the plus of the 12 volts, plus 12 volts, back to where we started, equals 0. So we got one equation, only thing we don't know is VY, so if we solve this for VY, take these other 2 numbers to the other side, right? So we get VY plus 2 equals 0, so VY equals -2 volts. So I named VY wrong in the first place, and I could have just looking at it, could have told you, so this is the high side, this voltage is higher over here, 12 volts. This is the 0 point for both of them. This one's only 10 volts, so we would expect current to flow downhill from high voltage to low voltage, right? And so I and Vy and I are both backwards, but that's okay. Okay, so Vy is negative 2 volts. And so what is I? How can we get I now? Well, we know Vy, the voltage across the resistor. We know Mr. Ohm tells us Ver, right? V equals IR. And so we can rearrange that to say I must be V over R. All right, so in this case, I equals Vy divided by R, which is 4. So Vy is negative 2 volts divided by 4 ohms. So I is negative half an amp. All right. If we had named I going the other way, it would have come out positive, but we would have had to write Ver as negative, V equals negative IR. All right, and so if you don't use passive sign conventions, current into the plus on your resistors, then you'll have to write V equals negative IR for your Ohm's law. But we did it positive. We did the equation right, Vy and I in the correct relationship to each other. They just have to be negative, right? And so that's okay. The negative 2 volts is just as good a number as 2 volts. Okay, let's go ahead and stop there.